Alright, let's start with the problem for the night. As usual, I'll read it out. Find all the solutions in vector x, which is a three-dimensional vector of the equation system ax 12x, where x is again a vector, where A is this matrix, and the sum of x1 and x2 and x3 is 1. Right, so before we actually start solving this, I would just like to explain a few key concepts. The first is something involving the word eigen, so eigenvectors and eigenvalues. So let's look at a simple example. This is a matrix 1, 2, 2, 1, and let's multiply this by a vector. So this is of dimension 2 by 2, and then we have a vector. This is of dimension 2 by 1. We expect this to be 1 times 1 plus 2 times 1, so that is 1 plus 2, 2 plus 1, and this to be the resulting vector. You can simplify this, and this is just 3 times 3. And this is a resulting vector. So this was rather straightforward. Something you can do is pull out the common 3 as a scalar product of this vector. And just for the sake of it, I'll write the entire thing down here again, just for the sake of clarity really. So we had a matrix, let's call this A, some x, and this gave us 3, 1, 1, and again x, where this was a vector. So this describes exactly what happened here in symbols. So whenever we have a matrix, a square matrix multiplied by vector, and if the resulting expansion or whatever the result of that is that vector itself multiplied by some natural scalar, then this natural scalar is called an eigen. So that would be E-I-G-E-N. I haven't written that very properly here. An eigenvalue for this matrix. And this vector would be called an eigenvector. Right. This is important. You can watch a lot of 3 blue 1 brown videos and a few others who have actually demonstrated why this is useful. But yes, it's quite useful that sometimes multiplying an entire matrix to vector is basically just a scalar multiplication on that vector. It's quite interesting. So that's what an eigenvalue and an eigenvector is. In this example, we notice that we have been given something similar. We have some A, which is 6, 4, 3, 6, 0, 9, 0, 8, 0. And you multiply this with x1, x2, x3. These are your unknowns, and that is 12, x1, x2, x3. Again, notice that this is a square matrix, and this vector is this, both x vectors, and this when multiplied with this is giving this scalar, and so you have something similar like before, and this would be called an eigenvalue, and this would be called an eigenvector. Yeah, so rather straightforward. Now the interesting property is that whenever you have such a equality, so you can go ax is equal to lambda x, where lambda is the real number or the scalar. What you can do is sort of pull everything to the left hand side, right? And you can then take the x common. Sorry, let me use that as a post multiplication instead. And when we do that, you should get a minus lambda I3 x. I multiply this so that this looks more like as the I would have 1 1, and you'd multiply that in, so you get minus lambda, because a minus lambda does not make sense, where a is a matrix and lambda is just, you can't subtract from a matrix a scalar. So to take x common out, you have to multiply this with the identity matrix of 3, because we're dealing with a 3-dimensional square matrix here. And this is equal to 0. Now notice that we are looking for non-trivial solutions, as we have been told x1 plus x2 plus x3 is not equal to 0, and neither of these, so since this is equal to 1, at least two of them must have non-zero values, right? So plus 1 or minus 1, something to cancel out. And therefore we can assume that within this this entire statement, this vector is not entirely 0. And so if this is not entirely 0, you expect this to be 0, or singular if you like. That is, the determinant for this would be 0. And this helps us a lot. This actually helps us solve the entire equation system. So in our case, lambda is 12. So we can go to A and go 6 minus 12, 4, 3, 6, 0 minus 12, 9, negative 12, again 0, 8, 0. And when you do this, so when we do this, we get negative 6, 4, 3, negative 12, 9, 6, 0, 8, negative 12. So we have A minus 12I3. Clearly, this now is a homogeneous solution. We can solve this using Gaussian elimination, or we can just multiply these equations however we like it. The cool thing is, since we have 3 equations and this is a trivariate system, we can actually do that very quickly. So that would be most ideal. So I can do something like negative 12, 4, 3, 9, negative 12, x1, x2, x3 is equal to 0, 0, 0. And you solve this, so that would be negative 6 x1 plus 4 x2 plus 3 x1, 6 x1 minus 12 x2 plus 9 x3, sorry, this is x3, and these are all equal to 0, and 8 x2 minus 12 x3 is equal to 0. To solve them parametrically as quickly as possible, just assume xt is equal to t, so that I can get x3 in terms of t and then substitute that upwards in the bigger equations. And from this we can get something like x3 is equal to 8x2 over 12, which is something like 2 over 3t. Yes. So if x2 is t, oh my bad, I hope they don't confuse this for negative. No, it's not negative. x2 is t, then x3 is 2 over 3t. And let's calculate x1, put it in any one of these equations. I'll use the second one. So that would be 6x1 is equal to 12x2 minus 9x3. That is 12t minus 9 times 2 over 3t. That is 12t minus 60. That is 60. That is 6x1 is 60. That is x1 is t. That's simple as well. So if you look at the solution vector, which is x, it looks something like t 2t over 3. Now we have been given something which is, my bad, that's not a very pretty looking sigma, is that if you go 3 times and you start at I is equal to 1, xi, that is 1. This can be expanded more simply to be said the sum of the 3 values of this are actually 1. If you do this, you can get the actual values. So you can go t plus 2t plus 3 is equal to 1, which is the same as 2t times 3 plus 2t over 3 is equal to 1, which is 8t is equal to 3, and t is equal to 3 over 8. I will leave these as fractions. If you're too, very keen on getting decimals, which some people are, you can always evaluate the result for yourself. That is 3 over 8, that is 3 over 8. And the last one is 2t, 3. So that is, since t is 3 by 8, and we need 2t by 3 for the last element, we can go 2 times 3 by 8. So that would be 3 by 4 by 3, which is just 1 by 4. So this is 1 by 4. Actually, these are very simple decimals, so we can do this. 1 by 4 is 0.25. 3 by 8 is, well, we can cut the half of 3, so that's 3 by 2 is 1.5. Then you can cut that in half again, that is 0.75. And then you can cut that in half again, and then that should be 0.375. Okay, so the answer is 0.375, 0.375, 0.25. So that's the actual solution vector x. And I think this finds all solutions in x that are exactly this. Remember, we cannot have any other solutions because it was just parameterized by t, and only one solution can add up to 1. Had this had another variable like s or s here and s plus 1, something like that, then we would have thought about varying it, but it does not. So this is a final answer. Yeah.